Well, students, we are at the end of the kinematics of rigid body. After learning the concept of rolling, let us try to find the radius of curvature of a particle or a point of a body who rolls on a horizontal surface. To find the radius of curvature, we have a mathematical formula. If a curve is given y as the function of x, after the concept of rolling of a rigid body, let us find the radius of curvature of the path traced by a point of a rolling body. Suppose a particle moves in such a way that it produces a curve given by this equation. The radius of curvature of this curve at any point is given as 1 by rho. Rho is the radius of curvature, is equal to d square y 1 dx square upon 1 plus square of the slope of the curve and the 3 by 2 power of the denominator. This is the mathematical formula. If the curve is known, each y coordinate of the curve is known as the function of x coordinates, then you can use this formula. This is a mathematical approach. But here, by using the idea of physics or a physical approach, we can find the radius of curvature of a particle by using the concept of centripetal acceleration. Let me discuss that. Let us suppose that the particle moves in a curve. The particle is here, particle P, moves with velocity v, suppose. It has the acceleration a. This is the velocity, this is the acceleration. You take the component of the velocity along the acceleration, or you may take the component of acceleration along the velocity. The latter is more appropriate because we want to take the component of the acceleration along the line of motion. This is the line of motion is given by the velocity vector, line of motion. A particle always moves along the tangent, or you can call it tangent. If this is the tangent, this is the normal. Without drawing the tangent, we cannot draw the normal. This is the tangent, this is normal. This t axis or tau axis is n axis. This tau cap, n cap. Tau cap is the unit vector of the velocity vector. And n cap is the unit vector in the outward normal. This is out, this is in, because somewhere we can have the center of curvature on the normal in this side. Well, we draw a circle which passes through this point of the curve, which represents by any equation. Let the center of the circle be C. How many circles you can draw? Through a curve, any point on the curve, countless circles you can draw. But we will be talking about only one circle, whose radius is rho. Rho is the radius, or you can write r, doesn't matter. When you split the acceleration along the tangential direction, this component of the acceleration is called tangential acceleration. Along normal direction, this component of the acceleration is called normal acceleration. Normal acceleration can be given as v square upon rho or v square upon r. This concept is borrowed from circular motion, concept of circular motion. Let me talk about the kinematics of circular motion for a few minutes. When a particle moves in a circle, say with velocity v, with some acceleration a, you take the component of acceleration along the velocity, you are getting the tangential acceleration because this is the tangent. This is the tangential direction, this is the tangent. Then you can draw a normal. This normal can pass through the center of the circle. Therefore, this normal can be called radius, a radial direction. This is outward radius, this is inward radius, and this is the radius vector. First, in circular motion, normal direction and radial direction are same. Geometrically, you can show that the component of the acceleration along the radial direction is called normal acceleration or radial acceleration. Since this acceleration is directed towards the center of the circular path, this is also termed as centripetal acceleration. And that centripetal acceleration or radial acceleration or normal acceleration can be written as v square by r can be written as rho. Rho is not the density here. Rho can be written as the radius of curvature. If you don't like this term, you can write r. So, if we know the velocity and know the acceleration normal to the velocity vector, that is the radial or centripetal acceleration or normal acceleration, then you can write this formula: ar is equal to v square by r or v square by rho, or rho is equal to v square by ar. This is the formula for radius of curvature or the path traced by a particle or a point having a velocity v and radial acceleration r at the given point. Let me apply this principle in general curve. This is a circular path. This motion is called circular motion. This path is a general path, or the particle is moving in a general curve, or called curvy linear motion. Circle is also a curve. Parabola also is a curve. Ellipse, etc. are the curves having different equations. In curvilinear motion in general, there is a tangent, there is a normal. The component of the acceleration along the normal is called normal acceleration, and that normal acceleration is equal to v square by rho. Rho is equal to v square by n. Rho is the radius of curvature. Let me write the formula of radius of curvature in more straightforward way. When a particle or a point moves in a curve at any point of time, its normal or centripetal acceleration is given as v square upon r or v square upon rho, where rho is the radius of curvature, the path traced by the particle at that instant or at that point of time. If acceleration of the particle is a, and the angle between the acceleration and the velocity with theta, angle between the acceleration and velocity, then tangential acceleration is a cos theta, and normal acceleration is equal to a sin theta. Using these two equations, we can find the radius of curvature by using the equations 1 and 2. We have radius of curvature is equal to the square of the velocity of the particle at that instant upon normal acceleration, that is equal to its acceleration into the sine of the angle between the acceleration and velocity vector. Let me use this idea to solve some problems using the concept of rolling. Take the example of a rolling body. On a horizontal surface. This horizontal surface, and this body moves with the velocity v, an angular velocity omega such that omega is equal to v upon r for pure rolling, a rolling body. The question is to find the radius of curvature of the path traced by this point P, this point Q. Points P and Q. This is the question. Our formula is R is equal to v square by normal component of the acceleration. V is the velocity of that point. To solve it, we need to calculate the velocity of this point, velocity of this point. We need to calculate the acceleration of this point P and acceleration of the point Q along which direction? Along the normal direction. How to calculate that? Let us find the radius of curvature of the path traced by the point P. Now the question arises, what is the nature of path followed by P? What is the nature of path followed by P? Is it circle? Is it parabola? Is it hyperbola? Is it ellipse? Is it cycloid? And I will show you that it is not the circle. Why? Because you may think that, oh, if you stand here, you can see that this is moving in a circular path. But when you say path followed by the particle, needless to mention, with respect to the ground level, with respect to the ground frame, with respect to a point fixed to the ground, say this point be O. This point you can take C. With respect to this fixed point on the ground, the path followed by the particle P or the point P is not a circle. With respect to the point C, if you stand on this point C, you can see that this particle moves in a circular path. However, with respect to this point, the particle moves in a different type of curve called cycloid. I am going to prove it. This is the horizontal surface. For rolling, if you assume the velocity of the center as v, omega should be clockwise. This point must be stationary at this instant, called instant axis of rotation. So v is equal to r into omega. This v is given. Therefore, omega should be equal to v by r for pure rolling. Let us take the top point. P. The radius of curvature is v square by normal acceleration. Here the path is like this. It is not a circle, and I will prove that this path is a cycloid. In the cycloid path, at this point, highest point, this is the tangent. Therefore, this is normal. Hence, we expect that this point P, when it moves in this way, with velocity Vp, this is the velocity Vp. Its acceleration should be in this direction, AP normal direction, or you can call it N. normal acceleration. To calculate, we know this, where Vp is equal to Vpc plus Vc, Galilean transformation of velocity. What we talked yesterday. Vpc is equal to velocity of p with respect to c is equal to r omega, and velocity of c is equal to b. If you add these two, you are getting the velocity of point P. This is r omega I cap plus v I cap, where r omega is equal to how much? V for pure rolling. So I can write r omega as v plus v. This is 2v I cap. We got the velocity of the point P. We got it. Equation number 1. This is equation number 2. Next, you need to calculate the acceleration. How to find the acceleration of this point P? Acceleration of this point P along normal direction with respect to c along normal direction is equal to acceleration of the point P minus acceleration of the point c along normal direction. But what do we want? We want this vector. Acceleration of the point P along normal direction is equal to acceleration of the point P with respect to c along normal direction plus acceleration of c along normal direction. Galilean transformation of acceleration. Since velocity of the point c is a constant quantity, acceleration of this point c is equal to 0. Along which direction? Along x direction, along y direction. Along x direction, its acceleration of this point P c is 0. Along y direction also, acceleration of the point c is 0. Y direction is nothing but normal direction. Therefore, along normal direction, the acceleration of the point c is 0, since it moves in a straight line. Since the central point moves in a straight line, it doesn't accelerate along the normal direction or along y direction. Therefore, this will be 0. Then you can write acceleration of the p along normal direction is equal to acceleration of the p with respect to c along normal direction. When you stand here, you can say that the p is moving in a circular path. Therefore, acceleration of the point P with respect to c along this direction is nothing but r omega square. In which direction? R omega square. So this is equal to r omega square in this direction. So APCN is equal to APN, that's equal to r omega square minus j cap. But what is omega? Omega can be written as v square by r. Omega can be written as v by r, square of this, so you can get v square by r. In which direction? Downward. So this point is accelerating down with this acceleration. This is equation number 3. Substituting the acceleration, normal acceleration, this is nothing but the normal acceleration of the point P from equation 3 and the velocity of the particle from equation 2 in equation 1. By using these equations, we can write r is equal to velocity of the point P, that is 2v square of this upon acceleration of this point P, that's equal to v square by r. Instead of or you write rho, because we have written r for the radius of the disk. So, you will get confused if you write r, or you can write r dash. So, better to write rho. So, rho is equal to 4 into r, answer. Acceleration of this point P is downward, that is equal to v square by r. Acceleration of P with respect to C in this direction will be equal to acceleration of C. Acceleration of P with respect to C plus acceleration of C with respect to ground, or with respect to this point, let it be O. This point is stationary on the ground. We need the acceleration of this point P with respect to ground, that is equal to acceleration of the point P with respect to C plus acceleration of C in normal direction. Since it moves in a straight line with constant velocity, it cannot have any acceleration along this direction. Therefore, acceleration of the center with respect to the ground along normal direction is 0. Therefore, acceleration of this point P along normal direction must be equated with acceleration of P with respect to C along normal direction. We know that when you stand on the point C, you can see that the point P is moving in a circular path, and its acceleration with respect to U along normal direction or radial direction is equal to r omega square, and omega is equal to v by r. Then you are getting v square by r in which direction? Down, negative y direction. So, knowing the acceleration of the point P along the normal direction, that is normal direction, inward normal, and its velocity 2v, substitute these two concepts or two values, the velocity and the acceleration, in the formula for the radius of curvature. You can get the radius of curvature of this path traced by this point P at this instant is equal to 4 times the radius of the disk. But its radius of curvature of the path traced by the particle, when you measure or when you are viewing with respect to this central point, is none other than the radius of the disk. But when radius of curvature, that word is given, needless to mention, with respect to ground, therefore, this is the path traced by the particle with respect to ground. This is the cycloidal path, but with respect to the center, the path is a circle. And how the path is a cycloid with respect to ground, maybe in the concluding problems.